double feature lecture of Prahladh. I guess you will take a break when it fits the lecture, so we don't know exactly when it will be. And okay, you're welcome to begin.
Can you hear me, or is it?
Yes.
Is it good? Okay. It's not it. But I'll be speaking today, and this morning lecture is going to be on codes, expansion, and high dimension expansion, connection between these three objects. So during my talk yesterday, we already saw that expander graphs have some amazing applications towards coding theory. We listed these. This was exactly the slide I used yesterday. The expander graphs are useful for constructing constant rate linear distance binary codes. They are useful for distance amplification in codes. They're useful to get linear time, unique decodable and less decodable codes. Let's look at two of these constructions, in specific the first two applications. So we had these show the expander codes can be used towards constructing constant rate linear distance binary codes and for distance amplification. Now, you can ask the question, is this all that you can get from expansion, or can you add this? Can you actually soup up these? Can you get these codes with even better properties than what's listed over here? For example, one thing which we would like to know is, which is an open question, can we get constant rate linear distance codes over the binary alphabet, which are also locally testable with a constant number of queries? I will define formally what testable means later on in the talk, but this is an open question. So what you want to ask is, we had expanders give rise to these sort of objects. It gives rise to constant rate linear distance binary codes. Can we further soup up this object with additional property of local testability? That's one question we could ask. The question is, there was this other application of expander towards distance amplification. You could take a code with small distance and out of it build a code with large distance. This is the construction of Alon, Brook, Nauer, and Roth. And once you come into the world of codes with large distance, you can immediately ask, can you now equip these codes actually with efficient less decodable algorithms? They have large distance. You can prove that these codes, there are some codes that are constructed in this object. Do they also have, can they come up with efficient algorithmic less decodable algorithms? And in both these cases, the reasons I'm sort of looking at them, in both these cases, expansion is good enough to prove the first two properties, but it's unclear if expansion suffices to prove these additional properties that we want. I would like to get these extra one, and we had a sort of vague notion that possibly if the objects that we were using were not just expanders, but had even better properties, say they were high dimensional expanders, then possibly we could soup up these constructions and get codes with even better properties. So for example, do high dimensional expanders come to the rescue in either of these constructions? So what we actually do know is in the latter, in the second of the applications, high dimensional expanders can in fact be used to get efficient less decodability, equip the code with efficient less decodable algorithms. So the basic construction of Alon, Brook, Nauer, and Roth shows that if you have an expander code, then you can get some distance amplification. And what we can show is if that expander graph was not only, it came from a larger object which had high dimensional expansion, then not only can you get distance amplification, you can actually equip it with efficient less decodability. You can come up with an efficient less decodable algorithm. The situation in the first application is not similar. We don't know, but it seems to be as if expansion is not sufficient. In fact, mere expansion is not sufficient to prove local testability. But if you want local testability, possibly you need something like high dimensional expansion. It seems to be lurking behind in this one. So what I'll actually do is I will not talk about the second one where we actually have a positive result. I'll actually spend the entire talk on the first one to show why possibly expansion helps in the constructing constant rate linear distance binary codes, why it fails to achieve local testability, just mere expansion fails to achieve local testability, and why high dimension expansion might come to our rescue and actually give us. So this is just sort of a wishful thinking right at this point of time, but I do feel that high dimensional expanders can play a role to answer this question, and most of the talk is going to be trying to tell why I think so. So, by the way, the latter result, one of us, so this is joint work with Irit, Tali, Inbal, and Amnon. So I'm hoping that one of us will talk about the efficient list decodability of the Allenbrook-Naur-Roth construction in one of the following weeks. So now let's go to the first one. So just to get this one said, let's give a quick short primer on codes and then come to the problems in hand. So what are codes? Is going to be the codes. We're looking at some arbitrary subset of the Boolean hypercube. So that right now I'm looking at codes over the Boolean alphabet. All of what I say can be generalized to larger alphabets. And then we work on codes. We are interested in two important parameters of the code: the rate and the distance of the code. So what's the rate? Rate is basically, it's quantitatively defined as this quantity. And informally, what it is exactly the number of information bits per symbol of the code word. That's what the rate of a code sort of conveys. And then you have the other important parameter of a code, which is the distance of a code. It's a minimum distance. It's a minimum Hamming distance between two distinct code words, between two distinct elements of the code. And typically, what we'll be using is fractional distance, which is d over n. And if a code has rate r, if a code is of block length n, it has rate r and distance delta. This is usually denoted using this shorthand notation. That it's an n, rn, delta, n2 code. The 2 refers to the fact it's over the Boolean alphabet. And what's of great interest is to construct codes with the best sort of trade-off between rate and distance. And this is still an open question. We don't know what is the best trade-off between, given a particular rate, what's the best distance you can get, and so we don't know this. What we do know is we do have upper and lower bounds which not yet match, and we can get codes with constant rate and linear distance. We do know these codes. We don't yet know how to get the best trade-off between these codes. Actually, what I will be talking most of, in fact, all the talks I will be talking about are not just an arbitrary code. We'll be talking about linear codes, so codes in which the set is not an arbitrary set, but it's actually a vector space over GF2. We are going to use the alphabet 0, 1 as the field GF2, and it's going to be a linear space over this vector space. So once it's a linear space, you can express the code succinctly using a generator matrix. For example, if it's a linear code, it's easy to show that if the code has, if it's an NKD2 code, then there must exist a generator matrix, a k by n generator matrix, such that the code is exactly specified by this, exactly images of the map xg. And similarly, if this is one way of specifying the code. The other way of specifying the code is via the parity check matrix. That is, if a code is if C is an NKD2 linear code, then there must exist a parity check matrix. These are basically the constraints. These are a set of linearly independent set of constraints which are sort of defining the code. The code is basically given by all those elements in 0, 1 to the n which satisfy the constraints specified by the parity check matrix. Keep these two in mind. These will play an important role in what I'm going to be saying later. And for linear codes, distance of a code can be much easily talked about as it's basically the weight of the smallest non-zero code word. It's the smallest weight of a non-zero code word in the code. And usually when it's a linear code, I'm going to denote it using these square brackets, NKD2. Just to get our hands a little more dirty, let's see a few examples of a few codes. These will be sort of the main characters for this talk I'm going to be saying. So one of the simplest of the codes is the set of even parity strings. Just the simplest linear code is the set of all n-length strings whose parity is even. It's not hard to see that this is a code. In the previous construction, it's a n-1, 2 code. Then we have the Hadamard code, which we talked about yesterday. This is the set of all evaluation of linear functions. It's a code whose block length is 2 to the k is some parameter. So block length is 2 to the k, and it's basically, it's all those codes, all those strings which are the truth table evaluation of linear functions. And linear functions is basically a function that satisfies f of x plus f of y is equal to f of x plus y. This is exactly the Hadamard code. And it's not hard to see that the Hadamard code has, it's a 2k, 2 to the k, 2 to the k minus 1 Boolean code. So this is code which we'll talk about. These are codes over the Boolean alphabet. We can naturally, so far we looked at evaluation of linear functions. We can begin looking at evaluation of higher degree functions. In this case, it's useful to go to larger alphabets. And the definitions I said earlier easily extend to larger alphabets. So we have these two, the famous codes, the Reed-Solomon code and the Reed-Muller code. The Reed-Solomon code is just the evaluation of univariate polynomials of a particular degree. And Reed-Muller codes is evaluation of multivariate polynomials of a particular degree. We keep these codes in mind and then talk about testability. This one. So let's go back to code. So we had a code, and we sort of saw that a linear code can always be represented by a parity check matrix. Now, it would be nicer for us to work with, talking about graphs and this one, it would be nice to come up with not with a matrix representation of code, but a graphical representation of the code. So we talk about the graphical representation of the parity check matrix. What do I mean by this? Given any code, the parity check matrix, you can naturally associate with it the following bipartite graph. So what's this bipartite graph? So this bipartite graph is just the following graph. Let me just do this. So if the parity, can people see the notebook I'm using over here?
Yes.
Yes. If the parity check is this n by n minus k matrix, we view each of these as these are the n minus k constraints. The code, the natural bipartite graph I'm going to come about is this bipartite graph in which this side has n elements, this side has n minus k elements, and these n elements will naturally correspond to the n coordinates of the code, and these are going to correspond to the n minus k constraints in the parity check matrix. And suppose you have one constraint, some constraint C5 is involved. C5 looks like it involves it has ones in the second position and say the fifth and the eighth position and zeros elsewhere. The corresponding C5 is going to be connected to these three, X2, X5, and X8. So it's just a graphical representation of parity check matrix. I'm saying spending too much time for nothing, for something extremely simple over here. So once we have this, here's my mouse. And this is in fact called the factor graph of the code. So given any code, we can represent it using this bipartite graph, which represents on the left-hand side, you represent the element, the code words, and the right-hand side represent the constraints. And what's the code? It's exactly all those x1 to xn such that every single constraint is satisfied. That is, each constraint, at every constraint, you look at the bits that participate in the constraint, they should sum up to 0. And this is exactly it says only those elements x1 to xn belong to the code. Because now we can turn the question around and say, so far we took a parity check matrix and we constructed a graph out of it. We can do the other way around. I give you a bipartite graph. Can we construct a code from this? And this is the most natural thing. You look at the code, you view the left-hand side as the elements. So you're given some bipartite graph, say G equals LRE, the left-hand side, the right-hand side, and the edges. And given any, the right-hand side naturally represents a set of constraints that capture the code, and the code is just, this is the most natural definition. I spell it out. That is basically, I'm going to take all strings of length L such that for every vertex, for every right-hand side vertex, which I call a constraint, you have that you have summation xu is 0, where u ranges over all neighbors of this vertex v. This is a natural code that comes. Given a bipartite graph, we can immediately define this corresponding code to it. So given G, there's CG, which is the code that arises from this. Unlike in the previous case, the constraints in R need not be linearly independent. The constraints in the right-hand side could have dependencies in them, in which case the constraint doesn't add any more feature. It's just going to check the same check, and we will see such codes later on. We will see codes in which the constraints are not necessarily linearly independent. And so this is a very simple description of a code. Now, once I give a bipartite graph, we get a code out of this. Good question to ask is, how good are these codes with respect to the two parameters we care for, with respect to rate and distance? So let's ask this question. So how good is it with respect, what's the rate of this code? We saw each constraint on the right-hand side reduces the dimension by at most 1. Hence, if the number of constraints is smaller than n, then the rate is at least n minus m by n. That is, each constraint reduces the dimension, so that's the rate of the code. So once we have, if the bipartite graph is an unbalanced bipartite graph, with an imbalance being that the left-hand side is much larger than the right-hand side, then that immediately tells us that the underlying code has positive rate. So rate, so far rate is good, but what about distance? So if this graph had, what we're seeing so far, if this graph has an imbalance where the number of constraints is far smaller than the number of bits, then we have rate. What about distance? Is there some more properties of this graph that will ensure distance of this particular code? And what we'll notice is, if this bipartite graph was actually an expanding graph, expanding from the left-hand side, then extremely well expanding graph, then one can actually guarantee distance. And what do I mean by expanding graph over here? We talked about regular expanders in the previous talks. I'm going to talk about bipartite expanders. So I'll say a bipartite graph, LRE, is an NMD delta alpha bipartite expander if it has the following properties. Before, n and m refer to the sizes of the two sides, and if you want rate, we want m to be smaller than n. I want the graph to be D left regular. The regularity from the left-hand side, it should be regular from the left-hand side, and let's call that regularity arity D. And furthermore, we want a lot expansion from the left. That is, for every subset, every not too large subset, every set of size at most delta n, the set of neighbors of this set should be at least alpha times the size of the set. So this is what I'll call an NMD delta alpha bipartite expander. And it's not hard to show that for every epsilon that you choose between 0 and 1 and any imbalance that you want, there exists a particular delta, an integer d, such that bipartite expanders of these parameters exist. And notice here, the important thing over here is you're going to get bipartite expanders in which the expansion factor alpha, which I mentioned above, is as large as d times 1 minus epsilon. The best expansion factor one can hope for is d, because that's the left degree. And this says you can get as close to d as you want to. And how close, it depends on epsilon. A simple randomized construction sort of achieves this. And there are, today we know of sort of explicit constructions which come close to this, which achieve this object. Right now, we'll just take the fact that such objects exist, and we'll show that once such objects exist, the underlying graph, the underlying code, the code that emanates out of this bipartite graph should actually be an expander. And that's not hard to see if you make one simple observation. So far, we're talking about expansion. We can then move on to something called unique expansion. So expansion refers to the set of neighbors of a given set S. Now I'm going to further take a smaller set and ask what are unique neighbors. Unique neighbors are, for example, in this graph, so I've drawn on the left-hand side S and right-hand side N of S, which is a set of all neighbors. And within N of S, it's a smaller set of vertices, which is a subset of N of S, in which each vertex over here has a unique neighbor in S. That is, all the other neighbors in NS minus US have at least two neighbors into S. We call this the unique neighbor S. And it's not hard to see that we'll ask, when is a graph, just like we defined bipartite expanders, we can also define bipartite unique expanders. And this is an easy exercise to see that if the neighborhood of S is at least D times 1 minus epsilon S, then the unique neighborhood of S is at least D times 1 minus 2 epsilon of S. This is because the neighborhood, you do a simple double counting argument and you get this. Let me just, is this clear for everybody, or should I just quickly, let me actually quickly illustrate the, so what we want to show is that n of S is larger than or equal to D times 1 minus epsilon times S, then this implies U of S is larger than D times 1 minus 2 epsilon times S. So let the proof of it is fairly simple. Let n denote size of n of S, U denote size of U of S is just a counting argument. So we know that the number of edges going out of S is D times size of S. This is greater than or equal to at least all the unique neighbors have exactly one edge going out of it, and all the non-unique neighbors have at least two edges going out of it. So this is already 2n minus u, which says u is greater than or equal to 2n minus ds, and that's d times 1 minus 2 epsilon. Yeah, so back on the slides. So have this. So to say once we have such a thing, once we have, so in other words, let's go back to this. So this says that in order for this last statement to make any sense, we need epsilon to be less than half. Otherwise, this is a meaningless statement over here. So I'm going to say is if we have a bipartite expander for some epsilon being less than half, so we have an NMD delta T1 minus epsilon bipartite expander, some epsilon half, then it's an easy consequence of the fact that it's a unique expander to show that the corresponding graph has this property. It is as block length n, the rate is n minus m by n, and distance delta n. We already saw the rate. So rate already follows from before, and distance is just an easy factor of this one. Unique expansion implies that every non-empty set S of size less than delta n has at least one unique neighbor. So any code word which we have, if it is a small weight code word, then it's at least going to have one unique neighbor, and the corresponding constraint will be unsatisfied. So this says that that can't be a valid code. So once you have unique expansion, you're going to have code. So these are these. So once you have expander graphs, you have these codes with constant rate and linear distance. It's quite amazing that Bipartite expander graphs give you this. So, and in fact, we know more about these sort of codes that arise out of these bipartite expanders. We know that they are actually, you can efficiently sort of unique decode them. These are the famous Sipser-Spielman unique decoding algorithm. What we want to now ask is further, can we soup up these expander graphs, expander-based graphs? Can we actually add local testability to them? Can we come up with these codes? So we have constructed codes which have constant rate linear distance. Can we also show that these same codes can also be locally testable? So what is locally testable? So code C is said to be locally testable, Q mu locally testable, if there exists a randomized tester that gets access to a received word W, queries it on at most Q locations and accepts or rejects W such that whenever it sees a valid code word, it's going to accept, and when it sees something which is far from the code word, it's going to reject with considerable probability. Once again, I sort of things, okay, I can't see the audience here. Is any?
Is it clear? Any questions?
Fine? Okay, no, it's too quiet from my end, and because I can't even see your faces clearly, so I don't know what's going on. Anyway, so this is what testability means. And what we want to ask is, so this is what testability means, and we want to construct codes which are testable with as few queries as possible. We want to construct codes. And what does means, in particular, it means we should have codes which are in which we have a lot of low weight dual constraints, because these tests which are checking whether the code is in the code or not code are these tests of size q, and so the code must have a lot of dual words. Particular expander based codes, if the write degree is also small, then they will have low weight dual code words. An actual question to ask is, we constructed these amazing codes with constant distance linear, constant rate linear distance. Are they also locally testable? Can you equip them with local testability properties? Can you actually show, furthermore, that these expander codes that we constructed using bipartite expansion of unbalanced bipartite expander graph, can you also show that they are testable with a constant number of queries?
Prahladh, can you say anything, any somewhat interesting upper bound on Q just from good expansion? You said we don't know how to get to order 1, but can we say anything at all interesting? I mean, that we don't have to look at all the bits?
No. So what's the question? You want to show, can we put an upper bound on how?
Can we give any, your goal is to make Q constant. And I'm asking,
so actually what we'll show is, for most expanders, the underlying expander code will require linear number of queries to test it. So it's actually, it fails to be testable in a very, very strong fashion.
Is this the question?
No, wait, it answers it, I think. So if this, I mean, we actually know that just being a good expander still doesn't get Q to be little of anything.
Yeah, in fact, yeah, so what I like is just expansion does not get it to you. In fact, what we'll see, what I'll show in the next few slides shortly is, most expanders, in fact, will most random graphs which are good expanders will have the additional property that they actually require omega n property. The testability will require omega n queries. Forget about constant queries. It requires linear number of queries to realize to test this one. That's what we're going to say. So basically, what I want to say is the following. We already saw that if you pick a random graph, a D left regular graph with these properties, with high probability, it's a bipartite expander, and hence the underlying code is also a code with good rate and distance. So that's the great news about these graphs, that a random graph you build this way has good rate and this one. But it comes with this added caveat that with high probability that the corresponding code actually requires omega n queries for local testability. It is strongly not testable. Not just constant, but omega n locally testable. So just expansion is not going to suffice. In fact, most expander graphs are actually going to have this require a large testability. They fail testability in a very, very strong sense. And so is the statement of this theorem clear? So it's stating that expander graphs are great to construct codes with linear distance and constant rate. But if you just pick a random expander, it's not going to be testable. It's in fact going to be strongly not testable. It's not going to be testable in a very, very strong sense. It requires omega n queries for testing whether it's a distinguishing between code words and things that are far from code words.
So Prahladh, let me hold you up on this for a second. What model do you use in order to generate these expanders randomly? Just the left guys select a random set of neighbors, or do you do something more sophisticated?
So just the left deregular would suffice, but notice that to show testability, so testability is a thing. Firstly, the code, if it does not have any low weight dual code words, it's not testable by definition, because testability, you first require low weight dual code words. So if a code has only large weight dual code words, then it's not. For example, the Reed-Solomon code has only large weight dual code words. You can't there are no short low weight dual code words. So that's a necessary feature for testability, which sort of says that this graph which you construct should not only be left regular, but also from the right it should have the constant degree. So that's the model I'm going to build a graph which is D left regular, and on most right constructions, so the average right degree is right degree is also small. And that's the model we put. Under this model, you can show this following this one. And actually, I'll show you the proof. It's actually strongly this one. Under most models, most random models which you're going to construct are going to have this property. They are going to be strongly not tested.
But Prahladh, if the right-hand side, I mean, the right-hand side is an average, I mean, that's just, you know, double counting.
That's just you, yes.
Yeah, but let's say you go for something like a configuration model. You really want to control also the degrees on the right-hand side. Would the statement, the bottom statement of the present slide remain true? So again, you generate bipartite graphs at random using some variation on the configuration model. Would it still be true that the last statement in this slide holds?
What's the configuration model?
So every vertex on the left has big D half neighbors. Every guy on the right has, you give it somehow, it's free choice. You make some choice of numbers. You make them regular or halfly regular, and again half edges. And now you match the half edges from the right and from the left. That's the configuration.
And let me tell you this. So what's going to happen in the proof is just the following fact. So you construct this graph. You take out any constraint from the right hand side. Let's go to the. Is the notebook back on?
Are you planning to show the proof later on?
Yeah, I'm planning to show the proof.
Yeah, when we see the proof, it'll be
If this
clearer.
takes you off, of course, then we can take it offline later.
No, but I was planning to do the proof either on slide or on this. It doesn't matter. So it's easier for me to tell what the proof is rather than go over the slides. So we had this bipartite graph. Is the notebook on or?
Yes, yes.
Yeah, we have this bipartite graph, this one, and we have the code C, which is defined as C of G. Now let's look at the constraints over here, C1, C2, Cm, and let's construct graphs Gi, which is basically exactly the same graph as before. It's L, but R minus I, and you remove the corresponding edges, the edges incident on I. So it's this. So it's the old graph, except you just remove this one constraint off. If it so happens that all these graphs, we know that G is a bipartite expander. If it so happens G1, G2, G, all of Gm are also bipartite expanders, which most models of construction are actually going to give you. That is, knocking off one, this one is not going to really change the expansion of the graph. Then, in all those cases, you can show that the underlying C of G, this is not tested. So any model under which this is going to be true, we're going to have this feature. And the proof basically is just this following observation. Let's go back to my slides. So what's the proof do? So it's, as I mentioned here, so a random graph G, is the slides back on?
Yes.
Yeah. So a random graph G has the property that for every constraint on the right, if you look at this new graph GV, which is L, the same left-hand side, right-hand side, you just knock off this one particular constraint, and EV is just all the other edges which are not adjacent on V. This will also be a unique expander. This will also be a unique expander with very high probability. Therefore, if you look at the new code, the code corresponding to this graph CV, this will also have very good distance. Very good distance. In particular, this code is a super code of the code which we are talking about. The code which the C code has this has this extra constraint. The one constraint has been removed of the code. Therefore, this is a super code of the code that you're talking about. So this is a code with good distance. So all elements in CV which are not in C are actually far from C. All elements in CV which are not in C are far from C, because CV is a code with good distance. Therefore, now I'm going to come up with this hard distribution of code words, which is supported on the union of all these CVs minus C. Basically, what we're going to do is basically pick one of the constraints at random on the right-hand side, violate that constraint, and satisfy everything else. That's the distribution of code words. Just the distribution of words we are going to come. This is certainly not a code word, but from what I have said so far, all of these words are far from the code, and one can show that actually, if you go over the construction, that there is no easy way of recognizing, because I picked this constraint that have been violated at random. It's a random element it's a random write constraint. It's not going to be easy to find out if there are no short dual constraints that this code participates in. For testability, we need a low weight code word. We not just need a low weight code word, we need a lot of low weight code words that are violated. And this will fail miserably for this object, and this will basically tell you that the codes that come out of these objects are not testable.
In other words, you're looking at words that fail precisely one constraint.
Yeah, I'm looking at the words at precisely one constraint. So I'm assuming here that I forgot to mention one other property. I want that after dropping a constraint, it still remains a unique expander, and all the m constraints are actually linearly independent constraints. This will be true if m is much smaller than n. This is always going to be the case. All the m constraints. So each constraint, dropping the constraint actually changes the code. CV will be different from CG of V. So if the randomized construction has this property, then you're going to get this tree. It's basically, I'm not going into the details of the proof, but what the proof is trying to understand, proof is trying to exploit is the following fact. That is, if you want to show something is locally testable, we need words that are far from the code word to violate low weight constraints. Low weight constraints. That's the only way a tester can detect it. But it can't just violate a few low weight constraints. It has to violate a lot of low weight constraints in order for the tester to be able to recognize this. And codes that come out of expanders, that's not going to be the case. There are going to be very few low weight code words that are going to be violated by these words which are far from the code. And because of that, any tester is going to fail to recognize that this code, the tester is going to just fail to distinguish between strings that are in the language and things that are far, in particular this particular distribution of code words. So this example, one can go into the details of the proof, but basically this is the construction, and most random models are going to have this property, and this shows why actually if you just have expansion, then it's going to fail to be testable in a very, very strong fashion. That is, you're going to have, if you put these things together, you can show that actually the number of queries required to test it is going to be omega n. You'll basically have to look at almost all the elements on the left-hand side, or at least a linear fraction of elements on the left-hand side, before you find out which is the right-hand side constraint that is being violated.
Prahladh, can I make one more comment? So no, I mean, usually the way people often describe the problem of finding good in our code is you're looking for matrices in which in your language, no short dependency among the rows exists. In other words, there is no small set of rows whose sum is 0. And what you're showing now is that for local testability, you need much more. Actually, you need that no short combination of rows, or every short combination of rows generates a word of large weight. You spoke particularly of weight 1, but this seems to be the...
Yes, exactly. And the proof basically formalizes this fact. That is, the random expander is going to have this property, and that's why it fails. So if you build an expander, this one, it's going to fail to be testable for exactly this reason. So what we would like to ask is, can I equip this expander graph with some more properties? So I know that just if I have expansion in this way, it's not going to be testable. Can we equip it with more properties in order to make the underlying code, the code that comes out of this bipartite graph, to be testable? That's going to be the focus one. What we'll do is, so the way we will go about trying to do this, we'll look at examples of So we do know some codes are locally testable. For example, the Hadamard code, the Reed-Muller code. We will look into their proofs of testability and show that underlying in these proofs, there is actually the underlying bipartite graph has some additional features to it, and we'll ask if those additional features will help us to prove testability in general. So come to that point, this is a good time for a break. So what we have shown so far is codes that arise out of expander codes. Expander graph, a random graph, is actually good, has great properties with respect to distance and rate, but with respect to testability, it actually fails to be testable in a very, very strong fashion. More precisely, we had this sort of theorem that is, it has good distance and rate, but with high probability, the code requires linear number of queries for any testability. And what we'll now see is, can we sort of soup up this expander with some more properties in order to make it locally testable? So to do this, we will look at existing codes which not necessarily have good rate and distance, but are locally testable, and see what is it that goes into proving their local testability, and see if we can understand something out of it. And that's what I'll do in the second part of the talk. So let's break for about half an hour or 20 minutes. Or
maybe just, how long is the second part?
it will be just around the same time, about 45
I
minutes.
suggest to break. Okay, I mean, half an hour seems a lot, right? Maybe just.
Yeah, so a 15-minute break, and we meet again. For what's the time right now?
Now it's
I could continue also, but it's possibly good. There's a natural break,
okay.
And we could.
So let's continue at 10 a.m. Would that be okay?
That should be good. Yeah.
Okay. Thanks. Just got going, no?
Usually teachers take 5 minutes and we did last night.